Half of my time as DevRel is answering the same question. What kind of finance can DeFi actually compute? So I answered it 3 times at once. 3 levels deep for a 10-year-old, an engineering student, and a PhD. Here's what's landed. You pick the one that fits. Last time we covered app-specific rollups. The time before that, the execution environment. Now we get to the part that matters for DeFi. What those 2 things let you actually build when using Cartesi. Most DeFi protocols today aren't doing real math. Today, I'm explaining what changes when DeFi can finally do the math finance was built on. Let's dive in. Remember that special computer from video 1? The one that does all the maths off to the side? Remember from video 2 how each app gets its own lane? All still there. Now, imagine you and your friends start trading sticker collections. Some are rare, some are common. You all want a fair price. There's just one problem. The calculator everyone's agreed to use can only count whole numbers. When you try to figure out a fair price for a sticker, let's say 2.5 times more valuable than another, the calculator just rounds down. Some kids pay too much, some too little. Nobody's happy. That's basically what's been happening with DeFi. Share blockchains can do simple counting really well, but the harder math, like pricing, ends up rounded down. Not because anyone wanted it that way. Cartesi gives this thing we call DeFi a real calculator inside the special computer. The kind grown-ups use to do taxes or the scientists to predict weather. Now the apps can do real math, real fairness, real predictions. Everyone can still check the answer because the calculator is still tamper-proof, but it's smarter. Most DeFi protocols are shaped by what the EVM can compute, not what finance actually needs. The EVM uses 256-bit integer arithmetic. No transcendental function, no standard library, no math.age. If you want EXP or LN, the functions you need for risk distributions for almost any continuous financial model, you implement them yourself with Taylor series approximations. Each iteration costs gas. Each iteration loses precision. So protocols cap iteration and ship a model that doesn't reflect what the academic finance literature actually says. Logistic regression for credit scoring, not really feasible on chain. You'll burn through gas before convergence. Monte Carlo for path-dependent derivatives, same. Numerical integration for implied volatility surface, same. So DeFi quietly drops these features or moves them to a centralized backend that completely defeats the point. But Cartesi changes the constraint. Your application logic runs inside a Linux environment with full RISC-V floating point support, native math libraries, and the entire Python and Rust scientific computing ecosystems. You import SciPy stats and call norm CDF. You import NumPy and run a Monte Carlo. You import QuantLib and price the option the way that the literature priced it. The output is deterministic. Every validator runs the exact same instruction sequence, and the whole thing is fraud-proof secure. Your DeFi protocol can finally compute the math it was supposed to compute. libm, Intel, MKL, Sleeve, Apple's Accelerate framework can disagree on the last bit of SYN or exp functions. For a system where every validator must produce the identical state transition or consensus breaks, that's fatal. Cartesi resolves this by pinning the execution environment. On top of it, the entire Python and C++ numerical stack runs inside the machine. NumPy, SciPy, QuantLib, stats model, scikit-learn, PyTorch when you want it. The operating consequences is that iterative numerical methods can become economically tractable. Newton-Raphson for implied volatility from market prices, viable. Monte Carlo for jump diffusion option pricing, viable. Numerical integration for value at risk, viable. Multi-period stateful credit models that update logistic regression coefficients as the new user transactions land, viable. The economic argument follows the dispute resolution model we covered last time. On-chain dispute cost is log n in computation size, with complexity of 1 on final execution. So a 10 million instruction Monte Carlo simulation and a 100 instruction integer addiction cost roughly the same in the rare worst case where someone challenges. Computation volume decouples from settlement cost. The constraint that shaped DeFi for the last 6 years, the gas-bounded computational envelope, is no longer load-bearing. Protocol designers can build around financial behavior, not around what the EVM can afford to verify directly. Real volatility surface, real adaptive market makers, real on-chain credit models. The math stack matches what quant teams have been using for 30 years. The verification stack matches what L1 settlement requires. They run in the same machine. So whether you're splitting stickers with friends, pricing an option with SciPy, or designing a stateful risk engine that updates with the market, The answer is the same. Cartesi gives DeFi the math it was always supposed to have. That was 3 levels deep on math for DeFi. Tell me below which version made the cut for you. This wraps the first season. Execution environment, app-specific rollups, and real DeFi math. 3 problems, 3 levels deep answers. If you want a topic for next season, drop it in the comments.